Swayam Prabha. Digital India. Educated India.
Hello and welcome to this Manufacturing Processes Technology Part 1 Module 45. A brief recall of what we did in the last module. We were actually talking about the optimum machining conditions by cost minimization, where we discussed about the various productive and non-productive costs, the times which are used for loading and unloading, which are otherwise non-productive times, and then productive times based on which there would be actual machining operation. And then we tried to optimize the cost, and based on that optimum cost we had a velocity for minimum cost and tool life for minimum cost as again related through the Taylor's tool life equation. Today we are going to look at just an identical model, but it will be the minimum time or maximum production rate model, which is really assuming that you have the time per piece of manufacture to be minimum, or the manufacturing time manufacturing rate or production rate goes to the maximum level as the manufacturing time per piece is low value. So let us now look at this model, which is kind of an alternate criterion used for determining the optimum conditions of machining corresponding to the maximum production rate, okay, which is inversely proportional obviously to the production time per piece. So as this time reduces, the rate should increase, and that is the fundamental assumption here that we make for determining what is going to be the optimum parameter. So the time of production of one piece will be defined as the non-productive time per piece plus the machining time per piece plus tool changing time per piece. So if we want to express this mathematically, the total time of production per piece TU can be defined as T1, which really was the non-productive time for the tool changing, the workpiece loading and unloading, so on and so forth, plus the actual time of machining, which was TC, plus again the tool changing time per piece, which was TD times or the number of times that the tool would be changed, which is actual cutting time by the tool life T. Okay, so this is the frequency at which the tool would change per unit workpiece, times of TD, which is the time every time there is a new cutting edge which needs to be deployed in the system. So if I substitute again the value of TC and TAC, which are more or less similar to each other, again assuming the situation where all these different machining centers have hardly any relaxation time or idle time, okay, as designed because of the optimum path of the controller and the rapid feed, etc. So this is again written as PL or pi LD divided by 1000 VF, and therefore TU can be defined as T1 plus pi LD by 1000 VF, which is TC, plus TD times of pi LD by 1000 VF times of 1 by T, which is V by C to the power of 1 by N. Okay. So that is how you define TU, and want to just optimize this time per unit component, minimize this so that the production rate goes to the maximum. So upon partial differentiation of Tu with respect to V and equating to 0, you get that condition of optimum Tu corresponding to maximum production rate. So, let us now do that derivation here, dTu by dV, which is actually equal to pi LD by 1000 F times of minus 1 by V square plus pi LD divided by 1000 F C to the power of 1 by n dV to the power of 1 by n minus 1 by dV Td equal to 0, and obviously from that equation again let us just modify this a little bit, and so therefore, this pi LD by 1000 F times of minus 1 by V square plus pi LD by again 1000 F C to the power of 1 by n times of 1 by n minus 1 V to the power of 1 by n minus 1 by n minus 2 Td is equal to 0, yielding to us a condition pi LD by 1000 F C to the power 1 by n times Td times 1 by n minus 1 V to the power of 1 by n minus 2 equals pi LD by 1000 F times of 1 by V square. So, these guys cancel each other and we are left with the condition V to the power of 1 by n equals C to the power of 1 by n divided by 1 by n minus 1 times of Td, or in other words the velocity of cut corresponding to the maximum production rate condition. Okay, that is why the subscript B max equals C divided by 1 by n minus 1 times of the total number of times needed to change one cutting edge to the power of n, and just substituting this value in the Taylor's equation Vt to the power of n equal to C, I can always find out what is the time corresponding to the maximum production rate. So, this is the minimum time, but the maximum production rate, and that equals to 1 by n minus 1 times of Td. Okay. So, that is how you define the optimum criteria for the maximum production rate model, just as we did in the earlier case for the minimum production cost model. So, let us actually now work on a problem where similar kind of a situation is arisen, and for that we would like to consider a lot of about 500 units of steel rods 30 centimeter long, 6 centimeters in diameter, turned on a numerically controlled lathe at a feed rate of 0.2 mm per revolution and a depth of cut of about 1 mm. These things are fixed for the cutting process. Only thing which probably can vary is the speed, and if we look at the tool life equation, it is given by Vt to the power of 0.20 is 200. 200 is the machining constant for the Taylor's tool life equation. T is the tool life in minutes, V is the meter per minute cutting speed or cutting velocity. The other data which are needed or given here is that the machine labor rate is about 10 units of currency per hour. Machine overhead rate is 50% of the labor rate. Again, grinding labor rate is similar, 10 units of currency per hour, and the machine overhead rates are about 50% of the grinding labor. Now, the workpiece loading unloading time is given to be 0.50 minutes per piece, and all the data related to the tools are provided. These are brazed inserts. Original cost of the tools are about 27.96 units of currency, and the grinding time is about 2 minutes. Tool changing time is about 0.50 minutes, and it has also been given that the tool can be ground only 5 times before it is discarded. So, basically we are talking about just using the tool edge for 6 times. Okay. So, 5 times it is used after regrinding and 1 time it is used as is when it was original and it was the first cut that it was executing. Okay. So, there are about 6 such processes which could be, or 6 times the process machining process could be carried out with one brazed insert, with a little bit of again labor cost, as you see here, the grinding labor rates and overheads have been mentioned here. And we need to now determine the optimum tool life, optimum cutting speed, so that it works on a minimum cost model or maximum production rate model, and then also the minimum cost and maximum production rate, which are obtained from the the conditions as given earlier, and also estimate time per component and the lead time, and similarly in the production rate model estimate the corresponding cost per component and the lead time. So, we start sort of using the formulation that we had learnt earlier in this particular case, and the first thing we need to gauge here is the optimum tool life and optimum cutting speed to minimize the cost per piece. So, CO is the machine labor plus the machining overhead cost, and as we know here the total cost is 10 units of currency per unit time given in hours, plus again 50% of the labor rate, which is again 5 units of currency, and because it is per hour, per minute, conversion can be made by dividing through 60. So, this comes out to be equal to 0.25 units of currency per minute. So, let us also try to estimate the CT, which is the actual tooling cost, and here the original cost of the tool per cutting edge would be important. Added to that would be the total amount of grinding effort, that is grinding time times of the grinding labor and overhead rates which is paid for the grinding, is to be added on to this original cost of the tool per cutting edge. So, the original cost per cutting edge obviously is the total cost of the tool, as has been given in the question earlier, is about 27.96 units of currency, and we have already said that this tool can be used for 6 times. So, per cut or per cutting edge, the total original cost would be divided or split up by 6, and then we add the grinding overhead and labor rate to it. So, the total grinding time is given to be about 2 minutes, and the total grinding labor and overhead rates are calculated as 10 plus 0.5 times of 10, again in the same manner, divided by 60. So, this comes out to be equal to 5.16 units of currency as the CT value, or the value of the original, the value of the tool per for one particular machining operation. So, we simply apply the minimum cost model. So, we obtained earlier the total tool life for this minimum cost model is 1 by n minus 1 times of C0 TD plus CT divided by C0. So, we record the n value from the Taylor's tool life equation as given in the question to be 0.20, and therefore, this is 1 divided by 0.20 minus 1 times of 0.25, which is the C0 value, times TD which was given as the tool changing time, which is 0.50 minutes, plus the total amount of CT value 5.16 units of currency divided by the total CO value 0.25. So, this becomes equal to 84.56 minutes, and if we similarly calculate the minimum cost criteria, the velocity at the minimum cost per piece can come out to be the machining constant, the Taylor tool life divided by the time for the minimum cost model to the power of n. So, in this particular case it would come out as 200 divided by 84.56 minutes, corresponding to the optimum tool life to the power 0.20, and this comes out to be 82.337 meters per minute or 82.3 meter per minute. So, this is how you estimate the velocity corresponding to the optimum cost model, and this is how you estimate the time corresponding to the optimum cost model. So, we also now use the or try to solve the second part of the problem, which is about the maximum production rate model. So, optimize tool life and cutting speed to maximize production rate. Here obviously T max could be obtained as 1 by eta to minus 1 times of T d. Refer back to the derivation that has been just made in the earlier module, and similarly this can again be written as 0.20 inverse minus 1 times of 0.50 the T d value, and that becomes equal to 2 minutes. Similarly, the velocity corresponding to the maximum production rate condition as obtained from the equation T max to the power of n inverse times c. So, this is 200 divided by 2 to the power of 0.20 makes it 174.11 meter per minute. So, that is how you estimate the T max and the V max corresponding to a maximum production rate model. We also want to determine the minimum cost per component, time per component, and corresponding lead time. So, let us look at that extent. So, minimum cost per component time per component and corresponding lead time. So, let us first calculate what is the total amount of cutting time in this particular case T c, and T c has been, as you already know, provided through the formulation pi L d times of 1000 V f, and the V value that we are using is corresponding to the minimum cost per component model. So, it is V min, and V min has been borrowed from step A of the earlier parts, where V min was determined as 82.337 meter per minute, and we can write this here as 3.14 value of pi times of the total length of machining, which is about 300 millimeters, 30 centimeter long. That is how the question recorded. In terms of the diameter of the in terms of the length of the workpiece, the diameter was 6 centimeters. In this case, you can record it as 60 millimeters divided by 1000 times of the velocity corresponding to the minimum cost model 82.337 times of again the feed, which is 0.20, and this comes out to be equal to 3.4325. So, if we want to determine the minimum cost in this particular case per component, this would be recorded as again the C0 T1, which is actually the non productive cost per piece, plus C0 Tc, which is the machining time cost per piece, plus the C0 Td Tac by T, which is the tool changing cost per piece, plus finally the tooling cost actual C1 Tac by T. So, in this particular case we calculate the CO as 0.25, which is the machine labor and overhead rate corresponding to the situation that has been described here, times of the T1, which is actually the non productive time consisting of loading and unloading of the part in minutes. So, in this case that is given to be 0.50 minutes per piece, the work piece loading and unloading time. I refer back to the question, times of or plus C0 again 0.25 times of Tc, which was obtained from this minimum cost criteria as 3.4325 plus 0.25 times of Td, which is actually equal to (0.50) minutes, again the time to change one cutting edge, times of Tac, which can be treated briefly as Tc. So, times of 3.4325 divided by T minimum, which came out to be in the last part A solution 84.56 minutes. And then finally, this is added on to the tooling cost that is used, which is about 5.16 times of the total Tc value 3.4325 divided by again the T minimum value here 84.56. Hence, the price per component comes out to be 1.197 units of currency per piece. Similarly, the production time per piece which is equal to the maximum production time per piece at the velocity which is corresponding to the minimum cost condition, and that is given by Tu equal to T1 plus pi LD divided by 1000 V minimum F plus pi LD divided by 1000 V minimum F times of V minimum by C to the power of 1 by n Td, and this becomes equal to 0.50 plus again 3.4325, which is this value here right about here as obtained earlier in this step, plus again the same value 3.4325 times of V minimum, which was also obtained as 1 by T minimum. So, T minimum was obtained as 84.56. So, I will just substitute that value here, 1 divided by 84.56 times of the Td value, which was again 0.50, the time to cut one or time to replace one cutting edge for the tooling operation. So, this is calculated as 3.95 minutes, and therefore, if we include the major setup time, which is a part of the ignore the major setup time, which is a major part of sometimes the total lead time. The total lead time is really in the time needed to make the 500 pieces at the rate of 3.95 minutes per piece, which makes it about 1976.4 minutes in totality. So, with the Taylor's tool life, we are able to estimate that corresponding to the minimum cost per component criteria, and optimizing the tool life, we have a lead time which is about 1976 minutes and a total cost per component which is about close to 1.2 units of currency per piece. In a similar manner, we can do the same for the maximum production model. So, let us actually now do this for part D. Part D asks about the parameters, including the production time per piece, or let us say the cost at the maximum production rate. So, maximum production rate model, you have to find out the corresponding rate, the corresponding cost of machining, and the lead time in this particular case. So, we have the first part is to sort of estimate what is the actual cutting time. So, considering the V max now, that means the velocity corresponding to maximum production rate, the total cutting time comes out to be equal to 3.14 times of 300 times of 60, the various length and diameter parameters of the workpiece, divided by 1000 times of 174.11, which is the velocity corresponding cutting velocity corresponding to the maximum production rate times of 0.20 the feet, and this comes out to be 1.623 minutes of time. And similarly, the production time per piece at V max can be recorded as the total amount of non productive time per piece T1 plus the total the cutting time of the corresponding workpiece on the machine Tc plus Td, which is the tool changing time per cutting edge, divided by the number of times it is needed for changing the cutting edge of the tool in a particular workpiece, recorded as TAC by T. So, in this particular case, I can put all these or plug all these values here. This T1 happens to be 0.50 minutes, the non productive time. This happens to be Tc, which has been calculated as 1.623 minutes, just about in the last step, time, plus Td, which is 0.50 times of TAC, again Tc 1.623 divided by T max, which is actually in this particular case 2 minutes as calculated earlier. So, divided by 2, and this is recorded as 2.53 minutes per component. Okay. So, if you consider the maximum production rate model, then the total time per component which comes out is only about 2.53 minutes, and therefore, if I wanted to look at the lead time again without really considering the major setup time of the machinery, it is just the time per component times the number of components to be produced, that is 2.53 times of 2.53 times of 500, and this corresponds to about 1264.6 minutes. And similarly, the total cost at the maximum production rate model comes out to be equal to again the non productive cost 0.25 times of 0.50 plus the total amount of cutting time, which is again total cost because of the cutting time, actual cutting time, which is 0.25 times the time of machining individual component, which is in this case 1.623 plus the total amount of time for tool changing. So, in this particular case, the tool changing time can be recorded as again 0.25 times of 1.623 times of 1/2 times of 0.50. This happens to be the optimum cutting time TAC or TC, 1/2, because this 2 right here is the optimum tool life, which is 2 minutes in this particular case, and this 0.25 again happens to be the 0.25, which happens to be the machine labor and overhead cost, plus the cost because of the tool changing operation and the total amount of tooling cost which is involved here, and this is 5.16 times of the total time of cut divided by the time corresponding to the maximum production rate, which is 2 minutes, and this comes out to be equal to 4.82 units of currency per piece. So, you can see here that corresponding to the maximum production rate model, we have been able to determine the optimum time of cutting, and then from that predicted the total time per component corresponding to the maximum production rate and the total cost per component corresponding to the maximum production rate. So, this is how Taylor's tool life equation can be suitably used to optimize some of the cutting conditions, particularly in high speed machining, etc., and it is a very useful equation as such for predicting some of these production rates or the costs of the components given some particular condition of optima. So, having said that, now I think we should look into some aspects regarding cutting fluids and why they are used. So, as you may recall that any liquid or gas applied directly to machining operation is generally done to improve the cutting performance. The two main problems which are addressed by the cutting fluids include the heat generation and particularly because of machining, that there is a shear zone and a friction zone where there is a lot of heat which is generated. So, this is one of the problems which are addressed, and the other problem is obviously the friction at the tool chip and the tool work interfaces, which again causes abnormal rise of temperatures in the cutting zone, and somehow by putting cutting fluids you ensure that machining operations become smoother. So, some of the other functions and benefits that the coolants or cutting fluids would provide would be to wash away the chips which are generated from the machining zone, particularly in grinding milling operations. You can also reduce temperatures of the work surface, and this is important for easier handling, particularly when manual handling components are involved. And then obviously you reduce the coefficient of friction at the chip tool interface due to the formation of a weaker compound at the interface due to some kind of chemistry between the cutting fluid and the tool surface, the tool surface as well as the workpiece surface. And finally, you protect the finished surfaces from corrosion by putting a layer of this cutting fluid which always flows into the finished surface from the working zone while it is being applied. So, what is some of the characteristics associated with an ideal cutting fluid? So, they should have a large specific heat and thermal conductivity, so that they can easily carry away the heat, thus lowering the temperature in the cutting zone. They should have a low viscosity, so that they are easily flowable, and maybe small molecular size. These are probably, they go hand in hand. Contain a suitable reactive constituent, be non-poisonous and non-corrosive, and also should be inexpensive and easily available. And having said that, now the cutting fluids can be classified really according to the functions that they are used in or they are put to. Some of the cutting fluids can be used as coolants, which are typically designed to reduce effects of heat in the machining zone, and some of them can be used as lubricant, where it is designed to reduce the tool chip and tool work friction. The many types of cutting fluids, typically water based or oil based, mineral oil based. The coolants are typically the water based fluids, which would have again a higher thermal conductivity, high specific heat. Again in the lubricants, they would have more slightly more viscous kind of fluid, and also they would typically be mineral oil based fluids. If we look at coolants, water is used as a base in the coolant type cutting fluids, and most effective of operation range is basically at high cutting speeds, where heat generation and high temperatures are very prominent problems, and these coolants are most effective on tool materials that are most susceptible to temperature failures, example let us say high speed steel, etc. On the other hand, lubricants usually are oil based, as I earlier pointed out, based out of mineral oil. They are more effective at lower cutting speeds, and they also help in reducing temperature in the operation, but they are slightly more viscous in comparison to the coolants, because they typically have to work out a layer of film which would form which would really necessarily provide the lubrication between the tool and the workpiece surface. So there are many advantages, particularly economic advantages of using cutting fluids. One is the reduction of the tool cost, another is the increased speed of production, again reduced heat and friction, so higher cutting speeds can be obtained, and probably maximum production rate conditions could be arrived at. Obviously reduction in labor cost, if you have a more uniform surface finish, then finishing costs come down drastically, tools may be able to last longer and may require less regrinding or less downtime or reduced cost per part. And then finally, reduction of power costs because of the additional advantage of formulating a zone which either acts as a lubricant or as a sort of a coolant, and reduces the temperature, so that you need not. So reduction of power costs, typically the cutting fluids ensure, if they are used as a lubricant, they ensure that there is a small layer between the tool and the workpiece, and obviously in that case the frictional effects are reduced quite a bit, so the frictional dissipation would also be subsequently reduced. And then finally, because of the reduced friction, less power could be required for machining. So with this I would like to sort of close on the machining module, and obviously the next step would be that once we have learned how to do the primary fabrication process in terms of casting, and then probably trying to machine the components so that they can come into an assembly, the obvious secondary manufacturing process which comes into your mind is how to join things together so that there can be a positional relationship between different components, and they can work out into machines or assemblies where there can be an input side which could be in terms of power or velocity, and there could simultaneously be an output side. So now the focus that we will have on this course from next module onwards would be typically on joining processes, and this would constitute for another 3 or 4 modules, beyond which we will like to end this course. So thank you so much for listening. I would look forward to talk about welding in the next module. Thanks.